Hi everyone. Today I'll be presenting my Capstone 11 project, that is DeepFER, which is Deep Facial Emotion Recognition. The goal of this project is to build an intelligent system that can identify human emotions from facial images, and the model classifies facial expressions into like 7 categories, that is angry, disgust, fear, happy, neutral, sad, and surprise. And the emotional recognition has been applied in this healthcare, customer experience analysis, and for education purposes, and for human computer interactions, and driver monitoring systems. And let us go through a little bit of project summary. And here I have the whole project summarized. The problem is essentially a multi-class image classification, where the problem is the input is a grayscale facial image, and the output is one of the emotions that are mentioned in the categories here. And the challenge here is to uh, that all of the emotions look almost similar to each other because of the highly imbalanced data, and also we need to make it easier for the models to understand, so that those emotions are clearly understandable by the motion uh, dataset models. And my GitHub link. And coming to the main problem statement, the objective is to accurately classify a facial image into one of the 7 categories is my uh, key objective and key challenge. And a few other challenges of my project also include class imbalancing, and similar facial patterns across the emotions, and variations in lighting, and variations in facial structure among individuals. Because of these challenges that I faced in the solution, a simple machine learning approach is often not sufficient. So, uh, uh, similar to the other modules, I've also used like 3 deep learning methods to overcome this problem. And let us deep dive. These are the libraries that I have imported for our whole project, and I've also used TensorFlow. And we have a data set that is locally stored, which is uh, a lot of images, all images. And I wanted to show what are the classes that are available, that are the 7 categories. And I split the records for training and test purposes. These are around a lot of images. This is an example that I wanted to show for the subplot, the sample images for each 7 categories. Coming to the total dataset count and column rows, there are a very vast number of images. There are around 35,000 images in all the folders, and within those 7 columns, 7 sections. And I split that into 80-20%. As you can see that in the 80%, around 29,000 images are in the training data set, and in the value images for test data, we have around 7,000 images. And coming to the data set info, as you can see that the height, width, and mode are all the same for each image. As you can see, file example also we have for the data sample information. And coming to that, we see that there are few duplicates as well when I try to find duplicates. And any null values for here for images, we need to see null values in the sense that if the image is any image corrupt or not. So I wanted to find out whether any image is corrupt or is any missing pixels in the 48 by 48 size image. And I found out that all images are readable and there is no corrupt image in the value. So as you can see, after splitting into training versus validation dataset for 80, 20, 20%, as you can see that the count of photos or images in each segment is here. The blue represents the trained dataset and the orange represents the validation dataset. This is what I've mentioned in the first view of my data information. And coming to the dataset and variables, we can see that there are 7 categories from 0 to 6 for 7 emotion classes. I wanted to find out information about the mean brightness, about how bright the image is from ranging from 0 to 1. So it's giving 0 0.4, 0 0.5 as a mean brightness for each emotion. This is what I mentioned in the variables description as well. And coming to the unique values, I wanted to check whether we have any unique values in the dataset. That is meaning that if there is any pixel value that is unique, or whether every image is falling in the same pixel count category. And coming to the data wrangling, I've taken 200 sample classes for each emotion, and I wanted to train that data in the sample data. And as you can see, for in the sample data, I found out the shape is 1400. I took this is 1400 because of each type. Yes, 200 we have for every class. 200 into 7, that is 1400. The size of data frame images for the sample data set. And the mean brightness, standard brightness, and max pixel, minimum pixels is the image details that we can find out. And coming to see that the data frame has the splitting into emotions, and we can see that the class weights of each uh, emotion. Coming to the data visualization charts, as you can see, the first chart shows about the training class distribution. Happy emotion completely dominates the dataset, while disgust is severely underrepresented for my dataset. And this also confirms that the all dataset is imbalanced. Coming to chart 2, this chart shows the validation distribution for my uh, data set, that 20% validation data set. As you can see, this is completely similar to that of the training data set only, which has happy as the leading value and disgust as the least dominant value. This confirms that the imbalance issue similar to the training data set is present also in the training data set. Coming to chart 3, this is a grouped comparison between training dataset and the validation dataset that are split across the proportionality. Coming to chart 4, that is a pie chart which shows the highlights of how much dataset belongs to each emotion. As you can see that 25% is combined for happy dataset and disgust is only leading having with 1.5. That is what I mentioned in the insights as well. Coming to the next chart, that is bar chart with uh, information that is for the brightness emotions and contrast chart. This shows that the different emotions show different visual patterns, which indicate that the meaningful information exists so that we can use this chart emotions in CNN machine learning model to learn and train the data. This is the same for the chart 6 as well for the pixel brightness, but that is distributed uh, between classes. Coming to the next chart, that is the image contrast, that is pixel standard deviation. As you can see that the heavy deviation is there for angry and disgust, where there is least deviation for surprise. Coming to chart 8, that is mean brightness by contrast. I've shown as a scatter plot where different emotions show different visual patterns, and each indicate that a meaningful information for the machine learning model to learn. Coming to chart 9, this is the average face expression for each emotion class. This is the average of 50 dataset images for the random sample. As you can see that each average face is very distinct. Like happy face is showing a curve, and sad and angry shows disgust face. Disgust shows neutral. Like that, there are sample images for each and every emotion type. Coming to next one, there is pixel intensity also regarding with the pixel intensity from 0 to 1 with respect to the density of emotion for each image. Next chart comes the training data set and the testing data set, that is 82% as I've told you earlier. And next chart comes the class imbalance ratios. How much if disgust is taken as a sample base value, how much times does the train imbalance ratio is with respect to the least amount of data present in for the training data set. That is what I wanted to show. And next comes the violin chart for the brightness distribution. As you can see here, the mean brightness and angry is split from negative emotions to positive emotions. Next comes the correlation map. Mostly disgust and happy face emotions are fear and surprise emotions are correlated to each other, and disgust happy disgust and fear are correlated to each other, and also sad and neutral are also correlated to each other, highly correlated to each other compared to the other ones. And next comes the pair plot for all the uh, emotions. Next comes the hypothesis. As you can see that we found we used three hypotheses for to show that mean pixel brightness differs from across the emotion classes, and the class distribution training set is non-uniform, which is that I meant to say that is imbalanced, and happy images are slightly higher than the brightness of the sad images. I performed appropriate statistical tests for each three uh, hypothetical statements, and all of them turned out to be rejected because I wanted to prove that is which are true which are true with respect to the p-value. And for the first hypothetical statement, I used one-way ANOVA test to test the three independent values, and for the second one, I used chi-square test. And for the third hypothetical statement, I used independent two variable sampled T-tail value test. Now comes to the feature engineering. The pixel value ranges from 0 to 255. So I wanted to normalize that to the value ranges from 0 to 1 for equivalent standard ratios. because normalization helps stabilize the gradient updates and improves training accuracy and efficiency also. So I use the data augmentation methods and techniques such as flipping and rotation uh, to to increase the data diversity and to reduce overfitting of data. This is what the summary of my feature processing. And coming to the ML implementation, in the first model, I used a custom CNN method, which is the first model to use a custom. I use the custom convolution neural networks that is built. This architecture contains batch normalization, max pooling, and layers, as you can see here, and convolutional layers as well. These convolutional layers uh, learn from the facial features such as edges and eyebrows, eyes, and mouth, so that the dimensionality reduces when retaining the uh, important information. And as you just a second, we can see, yeah, with the you can see the curve. As you can see the curve, it shows that the training and testing data and accuracy are almost similar and going the same path. We can see that the model learns stability and generalizes while learning. uh, Here we can evaluate p1 value, f1 value, precision, and recall values, which where we can see that these metrics are important because of the data set that is imbalanced. And coming to the second model, I used data augmentation, and for that I used the transferring learning allows us to leverage model with the CNN model with the large image datasets as well. This improves feature extraction and model generalization for dataset, and this uses Keras and reduced plateau models. And as you can see the results, that is improved in the validation accuracy compared to the baseline CNN model that we used earlier. This confirms that the model augmentation and transfer learning will contribute positively towards model performance. And this is the kind of a confusion matrix for this second model. And the phase 1, phase 2 epochs, I used 15 epochs for each. And coming to the third model, that is efficient net model. That is this is the best model that I got for the three models. And to train that, I used all the train data set and testing data set validation model. Uh, this is the final implementation, which uses advanced feature extraction that is combined with classifiers as well. Uh, as you can see here, the model comparisons with the other three values as other two models as well, the CNN model and CNN with augmented techniques. And now comes with the SVM model. As you can see, the validation accuracy is 33% for the CNN model, 34% for augmented CNN model, and 42% for the SVM model. So we can say that the SVM model is a best match for our model. And this is the confusion matrix for our model. And yeah, this is what I've told, that my model, the third model, is uh, the best model for our and in the evaluation metrics are accuracy, precision, and recall and F1 score, where accuracy tells us the overall correctness of our model, and precision Precision shows the measurement of the positiveness that is correct or not, and recall measure shows how many actual instances are identified, and F1 score will be balanced for precision and recall. So this is the mean SVM values for different emotions here. As you can see, for angry, disgust, for fear, happy, and neutral, sad, and surprise for all these 7 types. And I wanted to save my model for future analysis, the best model, SVM model for analysis. I saved that and I loaded to see whether to perform any sanity checks, that whether the best model is performing accurately or not. I've got the same confusion matrix as well. The sanity check accuracy is 60% now from 42%, as we checked earlier. And this is what my project concludes, that among the 7 data types, this project developed a facial recognition system to capable that is classifying in 7 different types of human emotions. And among the approaches that are tested here, the final model got the uh, most accuracy, and balance also between accuracy and efficiency. And the opening opportunities in healthcare, education, and customer and analytics, and intelligent human computer interaction will be useful for this type of methodology and techniques. Thank you.